Hi, and welcome to Module 4 in Video Lecture 3. In this one, having already gone through and discussed what a derivative is intuitively, what we're going to do is talk about what a derivative is formally. So sort of list a formal mathematical definition of a derivative and how it relates to the intuitive definition we've already done. Turns out, despite the sort of general worry about calculus, the definition of derivative is really straightforward once you understand the intuition behind it. So let's start with the intuition. So as we said in the previous few modules, we can draw a function like this, and we can draw a secant in the function like this, and the slope of the secant is defined like this. Again, this is just what we've done before. Okay, so there's the slope of the secant. Now, what we said in the previous modules was that as the distance between x2 and x1 gets smaller and smaller and smaller, the secant gets smaller and smaller, and slowly, eventually, in the limit, becomes the tangent line, right? So this secant up here becomes, in the limit, this tangent line right here. And the tangent line is the point at which the line just intersects the curve of the function at a single point. So this is the way of representing that mathematically. How do we make x2 and x1 get closer and closer together? Well, really it's a limit as x1 goes to x2. A nicer way of writing that would be to rearrange x2 in this manner. So we can write x2 equals x1 plus h, well, h is some number, some real number. In that case, this becomes x1 plus h minus x1 divided by h. And that is the same way of writing the slope of the line as the previous way, just replacing x2 with x1 plus h. Why do we do that? Well, now, since h is the difference between x1 and x2, and the limit as x1 and x2 are the same point, on the tangent line, h gets smaller and smaller and smaller and eventually goes to 0. So a derivative can be taken as a limit as this thing, taken as a limit of that thing as h goes to 0. And that's it. That's the definition of a derivative. So let's write that over again. The limit as h goes to 0 of f of x1 plus h, we don't need the 1 anymore, but we'll leave that in there just to remind you, divided by h. And that is the definition of a derivative. That's all there is to it. Right? That's it. You can write this again as f prime of x1, or it equals df of x1 dx1. Again, there are lots of ways of writing that. We did that in the last module, but they all mean the same thing, the derivative, and they all mean this right here. And that's really it. So limit of that thing, that slope, as the distance between the 2 points on the line goes to 0, or as h goes to 0. That's all there is to the definition of a derivative. There's nothing more complex or confusing. That's it. So when we go and calculate that at the next module, we'll go through and see how you can apply that definition directly using what we know about how to calculate limits. And if you're not familiar with that, you can go back and check out Video Lecture 2 again, which has stuff on limits. We're going to use what we know about limits to calculate that limit and compute the derivative from the first principles of a derivative, which are just that equation. And again, there's nothing fancy with the intuition. It's just the slope of the tangent line at a point. Okay. Now, there's a little bit of complexity here, not in calculation necessarily, but in understanding when the derivative actually exists. Not all functions have derivatives at all points, but we actually can understand when they do by going back to the same definition. When does a limit exist? Well, a limit exists when the limit coming from the left is the same as the limit coming from the right. Right? So if I have some function like this, right? You think back to continuity, this function over here wasn't continuous because the limit of the function coming this way
is this point here, but the limit of the function coming this way is this point over here, and they're not the same point, so the limit doesn't exist at that point. The same logic holds for the derivative. The limit as h goes to 0 must exist coming from the left and from the right. It must be the same. Practically speaking, there's sort of two aspects to this. One, the derivative must be, the function itself must be continuous. If it's discontinuous, the limit is not going to be, in general, it's not going to be the same from both sides. So for a function to be differentiable, it should be continuous in practice. Secondly, the derivative itself must exist, so the limit must exist from both sides. How do we use that knowledge practically? It comes up sometimes. For instance, let's take this function here. Right? That function might be x minus z absolute value. This point z, as you go further and further from, say negative, as you go further and further from z, you get more and more, you get less and less. Well, the function gets less and less. I'm thinking about utility, so I'm trying to say utility gets less and less. This is another type of spatial utility function, in which there's an ideal policy preference z, and as you get further and further away from z, your utility gets less and less. It differs from the quadratic one, only in that instead of having curvature like that, it's straight. Now, the reason we tend to use the quadratic one rather than the linear one is that the derivative doesn't exist at the point z. How do we see that? Well, the function is continuous, granted, but the derivative, the slope of the line over here, right? I should change color. The slope of the line over here is positive 1, but the slope of the line over here is negative 1. The slopes, because they're lines, this is sort of an exception to the tangent touching only at one point. If you have a straight line, the tangent line to that straight line will be the same straight line. So it touches at all points. But since the slopes are different and constant, up to the point z, the slope coming from the left is plus 1. The slope coming from the right is minus 1. That hits at the point z, and the slopes aren't equal at that point. Therefore, the derivative at the point z doesn't exist, because the slope coming from the left, that limit, stays 1 forever. The slope coming from the right is always negative 1 forever. They never equal, so therefore there's no derivative at the point z. We say this is not differentiable at the point z. Differentiable here means the same thing as derivative. It means able to take a derivative. Differentiable. Differentiate means take a derivative. Same word, same different words, same idea. So certain functions don't have derivatives at all points, but notice that this function has a derivative at all points other than z. The derivative down here is 1. The derivative over here is negative 1. So this is plus 1, and this is negative 1. These derivatives exist at all points except for z when no derivative exists. In general, we say functions like this have kinks, and functions with kinks at certain points don't have derivatives at those points. So you'll see often in political science and economics and so on, the functions used be more like this, which have very similar properties to this, except derivatives exist at the point z, because if you notice this function here, the derivative is getting less and less and less, the slope is getting less and less and less as you go further and further towards the top, and continuously moves towards 0 at the very top. So that's a smoothly varying derivative, and it exists at all points, so it's easier to deal with mathematically. This function is harder to deal with mathematically because the derivative does not exist at the point z. You might ask, why then use it ever? Well, this function here means that the further and further you go away, it's increasingly bad. So the marginal change in badness effectively is increasing as you move further and further away from z. Policies that are really far away from you have substantial differences between each other in terms of your preference, as compared to policies close to your ideal preference, which have minimal changes between them. This one over here is more smooth. The linear one is more smooth and changes away from and the difference between any two say units away from your best utility is the same no matter how far away you go. In other words, moving from here to here, say, is the same loss of utility as from here to here. In contrast, over here, moving from here to here is a minimal loss of utility. Moving from here down to, oh, I didn't draw it far enough, down to here, or here rather, is a bigger loss in utility. So the quadratic loss tends to mean that the more extreme policies are increasingly bad for you as compared to the less extreme policies, whereas the linear utility, the linear loss function tends to mean all policies are equally bad for you as you move away. That's an aside though. Thing to take away from this is that one, the derivative definition is straightforward and it follows directly from our intuitive understanding of tangents and secants and instantaneous change as compared to discrete chains. And two, functions have derivatives as long as they're continuous and don't have either kinks or odd behavior at certain points. So for instance, functions that have behavior like this, that would also not have a derivative at 0 because the slope over here is decreasing infinitely, the slope over here is increasing infinitely, so there's no derivative at 0. So functions with kinks or functions with odd behavior at certain points won't have derivatives at those points. But other functions will have derivatives, and we'll see how to compute them as we go on in the course. Thank you very much.